The measuring transformer is the current transformer. All right, let's talk about it now. Okay, now regarding current transformers, hopefully the explanation here is clear to you. Okay, as for the current transformer, which is the airplane transformer, the idea is quite simple. The current transformer is one of the types of instrument transformers, which are the measuring transformers we talked about a little while ago. Nice. The current transformer is used to step down the current or to reduce the current values from higher values to lower values, which can be handled by measuring devices and protection devices. The idea is simply what happens, let's say you have, for example, one of the feeders, for example, a 13.8 kV feeder. Let's say we have a medium voltage feeder or 11 kilovolts, if you're talking about Egypt or the UAE, whatever the case may be. Let's say you have a single bus, single breaker scheme, meaning you have a bus bar, all right, and then you have it coming out from the bus bar like this, all right, and then it goes out like this with my feeder. Very nice. Okay, initially, of course, here we have what we call the bus bar, and here we have what we call my feeder or my line or whatever it is, the supply, regardless of what it's connected to. It could be connected to a generator, it could be connected to a transformer, which we might call a trafo. It could be connected directly to a load, it could be connected to a capacitor bank, and so on. So regardless, for me, in the end, what is it? It's a feeder or a supply, right? Good. Okay. Now, the current transformer, guys, for me, its connection can either be with a current transformer before the breaker, or there can be a current transformer after the breaker, or there can be a current transformer on both sides before the breaker, and after what? After the breaker. Very nice. Okay. This current transformer, any device or anything you use to measure the electric current, you must connect it in series in your circuit, meaning in series in what? In series in your circuit. I'll do. Great. Very nice. Okay. I will overlook the idea of the types of current transformers or their shapes for now. I will give you a very simple form where I come and do what? I come now and say, well, I want to connect it here in series. So I come first, I am coming out from here like this, for example, before I go to the feeder termination. Let's say this is the feeder termination at this point here. This is the feeder termination. These are the terminals where my cable connects. So before these terminals, what do? Before these terminals, I come and, for example, remove this part like this, and then I start to connect my current transformer here in its place. So for example, my primary is usually just one turn. So I have removed this part and installed the current transformer in its place. Then I connected the current transformer to the feeder termination, or I connected it to the feeder termination where my three-phase cable system will be connected later. All right, that's great. Great. So this is my primary. Why? Because this is where the current I want to measure will pass through, so it's part of it. You have at the beginning and end of the transformer, which consists of two circuits, primary and secondary circuits, right? Great. So I have connected the primary in series in my circuit to measure the current. Now, the secondary will be here. All right, that's great. Let me take you back in memory and refresh our memory together. Now, I'm asking you, where should the number of turns be greater, here or there? We all know the law that governs the turns ratio, which states that the primary current to the secondary current equals the secondary turns over the primary turns, meaning the current is inversely proportional to what? The current is inversely proportional to the turns ratio. Therefore, to reduce the current from a high value, which could, for example, reach here, say, 1,000 amperes, to convert it to 1 ampere, it means you do the opposite. As long as the current here is greater than there, the turns ratio here will be greater than what? Greater than there, because the relationship, as you can see, is inversely proportional to each other. This means the relationship here is inverse between the current and what? Between the turns ratio. All right, good, very nice. Let me, if I may, talk about some details, but just to avoid overwhelming you with too many details, I can also clarify this for you. I will explain where he got it from, but just listen to us. The important thing is that you know the current is inversely proportional to what? Very good. So I placed a number of turns here to reduce the current. Therefore, the number of turns here is greater than the number of turns in the other part. Very nice. So this is my connection. Great. So now, engineer, you know that the exciter allows the electric current to pass here. The whole idea is that it generates the magnetic field. And when you bring it closer, it starts to create what we call your magnetic field lines. These lines begin to cut through the coils, and consequently, it generates a current on the other side as well. Very good. So as we know, the resistance of the conductor equals Rho over A, which is the resistivity of the material of the conductor over the cross-sectional area of the conductor. This means that if you take any voltage source and connect two resistors in parallel, what happens? The whole idea is if I tell you that this resistor is 1 ohm and this resistor is 10 ohms, in this case, the total current, most of this current, a large portion of it, will flow through the 1 ohm resistor, and a smaller portion will flow through the 10 ohm resistor. It will act like a current divider based on the resistance value, meaning the lower the resistance, the more it will draw the larger share of the current. The same exact concept applies to the lines or flux lines you have, which are the lines. Your magnetic field also has a law that controls it, which is also called R. But here, this R is the reluctance. This reluctance is the resistance to the flow of my magnetic field or the lines of the magnetic team, and this creates L on the mu node in mu R in the area. We would like to see you in the area. All right, so the L is the path length that it will travel through, and you have the L as the cross-sectional area, and mu node times mu R. What is mu in general? Mu is what we call the permeability, similar to permittivity. The basic idea here is that now you have air, and its mu R is considered to be 1. All right, the mu R is considered to be 1, so the air has resistance or reluctance to the flow of flux lines. This reluctance equals L over mu node times the area. Okay, so what does this mean? What happens is that most of the flux lines that are generated get lost. Where do they get lost? They get lost due to the resistance of the air. All right? Very good. Just like the concept in a conductor where you have power losses, right? So what happens? They tell you, okay, then I will think of something else. What is this other thing? It is that I will bring here a material called low reluctance material, meaning its reluctance is low. This is achieved by having its MUR greater than 1. So of course, the more the denominator increases, the more the reluctance decreases. This material is our iron core, the core that is referred to as the iron core, which is made of something called, and I will talk about it in detail later, a material that is easily magnetized because its reluctance is low. This is to apply the same concept as the conductor, to make it go in the easiest direction for it in terms of what? In terms of its resistance. So where does it go? It goes in the direction. It goes in the direction. What direction? The core. Beautiful. Excellent. All right. Now the current has changed from 1,000 amperes to 1 ampere. Where do I connect this current? It goes here and connects here to what we call the burden or your load. And this load can be one of two things. Either it is the metering device, or it can be the protection device, which is either the measuring device or the protection device. These two devices can be either analog or IED, intelligent electronic devices, which are digital devices. Electronic devices to digital. What? Digital devices. Great. So in simple terms, this is the composition of the current transformer. The current transformer is one of the types of measuring transformers. And for static machines, its purpose is to reduce the current to interact with other components, values which can be handled by metering and protection devices. The second thing is that it is any such that its primary winding is connected to your power network, and its secondary winding carries the reduced current that you connect to your load, whether it's a meter or a protection device. So here you are dealing with lower values, which makes it safe for you and the equipment present. All right, great. Now let's talk about each component present in the current transformer. First, I have the primary winding. I will discuss the primary winding in the context of the type of current transformer because it determines for me, the core also has two types, one called metering and another called protection. Then the secondary has two types of polarity. And we will also discuss each component individually. I will address each unit separately here. And finally, I will talk about the specific board of the current transformer